Hello students, welcome to Inside Physics. In this session we discuss about phasors in alternating currents. A phasor is a rotating vector which is very useful in analyzing the alternating circuits. In alternating circuits we all know generally the potential difference creates the current in the circuit and whether they are in same phase, is there any time lag, that we already discussed when we have the alternating current through a resistor in the previous video. Here we introduce a concept of phasor. Why we require these phasors is to analyze the alternating current circuits and what is the phase difference. FA, this represents phase and this is vector. So a vector which tells about the phase difference between the potential difference, voltage and current. So a vector which tells about phase is called a phasor. So here the phasors are important and how we go with them. In the previous video we have seen that there is no phase difference between voltage and current when we have connected the AC source to a resistors. There is no time lag. So here we have taken the phasor diagram for a resistive circuit. AC source is connected to a resistors. So this is the vectors. This is voltage vector and see, this is current vector, this is voltage vector. Both are in the same line. That's why they are shown in a single line. This is a current vector and this is the voltage vector. This vector, actually this phasor is not a vector. So it is an imagined vector where the values, the mathematical values, scalar values will actually oscillate. The amplitudes and phases are harmonically oscillating and the harmonically oscillating values will actually give a picture of sinusoidal curve. So to represent the phase difference between the current and voltage in an alternating circuit, we have introduced the concept of a phasor. Okay. So this is the vector and this is current vector and this is voltage vector. These two will rotate in this direction like this, in this direction like this. So when they are rotating, see the current vector, when it is rotating like this, it is coming here to here in the positive direction and the value will be coming from maximum to 0, again to here in the negative direction, 0 to maximum, again from maximum to 0, 0 to maximum. So oscillating in the magnitude wise and the direction wise in a sinusoidal way. So here when they are rotating in a combination, both vectors, see what we get as a graphical picture, that is the second picture. When these two vectors are rotating like this, we will get a graphical picture like this. See, this is the phase 0, pi, 2 pi and so on. This omega t is nothing but phase at any instant, and here the current is shown in black dotted lines and the voltage is shown in red dotted lines. If you can observe this resistive circuit analysis, here the minimum is achieved at the same time and both current and voltage have come to the maximum at the same time, and here you can say this is omega t or you can say t1. We have taken this time t1, that means we are analyzing the current and voltage at a particular time t1, that is instantaneous current and voltage. So here they have come again to the minimum at the same time without any phase difference, and again coming to the maximum value on the other side, negative side, opposite side at the same time, and again they have come to 0 at the same time, and the phase is same at all points. So the phase angle between these two is 0. So in this way the phasors can be understood, and we can actually have the phase difference between current and voltage. If you take an inductor and capacitor circuit, when the AC source is connected to an inductor, there will be a phase difference between the potential difference and the current may be lagging behind the voltage by a phase of pi by 2. If you take a capacitive circuit, the current will be in advance to the voltage, so the current will be in advance and there will be a phase difference in the capacitive circuit, unless here this is a circuit only which is having a pure resistor and nothing else. So in this circuit there is no phase difference between voltage and current. So see here, this Im sin omega t1 is the maximum value at any instant. That means here the time 1, t1 is the instant of time, and Vm sin omega t is the voltage at any instant. Here the Vm sin omega t1 is the voltage at time t1. This is the current at time t1. So the vertical components will give the voltage and current at a particular instant. Okay, what we know from the previous sessions, Vm is the maximum amplitude. Vm sin omega t1 gives the voltage at a particular instant. So in this way the vertical components will give the voltage and current at a particular instance. So whenever this is a rotating vector, it rotates with an angular frequency. A phasor, this is the phasor, rotates at an angular frequency omega, and I have shown this in an anti-clockwise direction. So and this is rotating. How it will rotate? It will rotate about the origin. If you take this as an origin, this will rotate about this origin. So a phasor is a vector, rotating vector about the origin with an angular frequency omega. So this is how we understand phasors. This is a simple and interesting concept through which we can understand the current and voltage behavior in an AC circuit.